Chapter 5. Exponents and polynomials. Section 5.1, exponents. First, we're going to look at natural number exponents. Then we'll look at integer exponents, then rational exponents. So first, suppose I have, well, let's say 2 cubed. Then this is my exponent, 3, and 2 is my base. And well, it's going to equal 2 times 2 times 2. The base will be multiply the exponent number of times. So let me give you the definition of, well, let me first give you a notation. If I have any base, then a base to the power 1 is just the base. Okay, so now let me define bases to some some whole number exponent. So first, let me assume that the base is not equal to 0. Then any non-zero base to the power 0 is defined as 1, so long as the base is not equal to 0. Then I'll define a base to the power n plus 1 as equaling the base times the base to the power n for any whole number exponent n. So let me give you some properties. For exponents, let me assume that the base is not 0. And, well, I guess I'll have more than one base. So assume b is not 0 and a is not 0. So these will be two differing bases. Then a base to the power m times b to the power n is equal to the base b to the power m plus n. So if you have the same base and you multiply, then you just add exponents. Next, b to the m to the power n. So if you have a base to an exponent raised to an exponent, then you just multiply exponents and you keep the same base. Next, suppose I have some base b to the power m divided by b to the power n. And then this is just the same base b, but you subtract exponents, m minus n. Next, suppose I have two bases, a to the m times b to the m. So I have two different bases. I'm multiplying them together, but the exponents are the same. Then I can multiply these bases together and raise them to the exponent. Similarly, if I have some basis a to the power m over another basis b to the power m, then this is the same as a over b to the power m. And of course, b is not 0. You don't want to divide by 0. Okay. For these other ones, I guess b could possibly be 0, so long as both sides of the equality exist. So these still hold with the base being 0, except for, of course, if the exponents were also 0. So that's why I assumed in the previous cases that the bases weren't 0. Next, b to the power 1 is just b. b to the power 0 is 1. And let me explicitly say that the base can't be 0. Next, 0 to the power m is equal to 0. This is so long as the exponent is not 0. 1 to the power m is 1. 1 to any power is 1. And, well, we'll see this more in the future. B to the power negative m is equal to 1 over b to the m. Definitely here you don't want the base to be 0. So you're not dividing by 0. And maybe I'll write out the last one. B to the power m over n is equal to the nth root of b to the m. So long as you can take the nth root of b to the m. Okay, so long as the right-hand side exists. Let me do some examples. On page 184, suppose I do problem number 1. In exercises 1 through 12, identify the base and the exponent of the exponential expression. So 3 to the power 6. So the exponent is 6 and the base is 3. Let me do problem number 3. Negative 3 to the power 6. In this case, the exponent is 6, but the base is 3. Note: negative 3 to the 6 You multiply 3 6 times, and then you negate. Do problem number 5. So note the following. -3 to the 6. The exponent in this case is 6, but the base is -3. So in this case, I have -3 to the 6 means that I multiply -3 6 times. Actually, so note, -3 to the 6. 1, 2, 3, 4. 2, 4, 6. Okay, so notice the difference between the two is that in problem 3, the base was 3, but in problem 5, the base is -3. So if you wanted the base to be negative, notice that, or that I have to put a parenthesis. So if I wanted this whole quantity to be the base, I need a parenthesis. Otherwise, this negative out here will not be included in the base. So if you wanted to include the negative in the base, you would need a parenthesis. Otherwise, it wouldn't be included. Let me do problem number 7. Negative minus 5x to the 7. So in this case, the exponent is 7, and the base is -5x, just like in problem number 5. Let me do problem number 9. (5y) to the power 7. So in this case, the exponent is 7, and the base is 5y. Let me do problem number 11. (-5y to the 7). So notice the difference between number 7, number 9, and number 11. So in this case, the exponent is 7, and the base is y. So the y is going to be multiplied 7 times. And then we multiply by -5. 13 minus -7x to the 5. So the exponent is 5, and the base is -7x. Wait. I'm sorry, that was 11. Actually, that was problem 12. Yeah, that was problem 12 I just did. Let me do problem 13. X squared x cubed y to the fifth. In exercises 13 through 36, simplify as far as possible using the product rule. Okay, so let's just use these properties of exponents. So I have the same base, x, add exponents. 2 plus 3 is 5. I have the same base, y, add exponents. Well, recall that y is the same as y to the first times y to the fifth. 1 plus 5 is 6. And that is your answer. Let me do problem number 15. (16) x squared x times x. Well, I have the same base x, so I add exponents. So I have x squared times x times x. Well, x is the same as x to the first, and so I have x squared times x to the first times x to the first. Same base x, add exponents. 2 plus 1 plus 1, 4. And so this is equal to 16x to the power 4. Let me do problem number 17. X over y, times x squared over y times x cubed over y squared. So I have the same base, x, and I'm multiplying. So let's multiply x to the first times x squared times x cubed. Add exponents. 1 plus 2 plus 3 is 6. So x to the power 6. Y, well, again, I have the same exponent. I'm multiplying. And I have the same base y, so I add exponents. Y the first times y the first times y squared. 1 plus 1 plus 2 is 4. I cannot simplify this any further because x and y are differing bases. Problem number 19. X squared over y cubed. X to the fourth over y squared. X over y is equal to, I have the same base, so let me add exponents. 2 plus 1 plus 4 plus 1 is 7. I have the same base y, add exponents. 3 plus 2 plus 1, 6. So x to the 7 divided by y to the 6. Let me do problem 21. Three y squared times 2y cubed let me multiply. 3 times 2 is 6. I have the same base y, so and I'm multiplying, so let me add exponents. 2 plus 3 is 5. So 6y to the fifth. Let me do problem 23. Seven a squared minus 2a cubed is equal to, well, let's do, raise each of these inside the parentheses to the power 2. So 7 squared times a squared. A negative 2 cubed times a cubed. Oops. Which is equal to 7 squared is 49. Negative 2 cubed is negative 8. So let's multiply. Positive times negative is negative. 49 times 8 is 392. I have the same base a, add exponents. 2 plus 3 is 5. And let me just check. That's 32 and 72. Yeah. Okay, so negative 392 a to the power 5. Let me do problem number 25. P times p to the 4 times p to the 6 times p to the 5 is equal to, I have the same base, p, so I add exponents, and I'm multiplying, so I add exponents. 1 plus 4 plus 6 plus 5, 16. So p to the power 16. Let me do problem 27. Let me raise everything inside the parentheses to the power 3. So this is 6 times a times negative 2 cubed times a cubed. 6a. Negative 2 cubed is negative 8 times a cubed. Positive times negative is negative. 6 times 8, 48. I have the same base a, so let me, and I'm multiplying, so let me add exponents. 1 plus 3 is 4. So negative 48 a to the 4. $29 y times 3y is equal to 1 times 3 is 3, y times y is y squared. Do problem 31. Negative 3x, negative 2x. Negative times negative is positive. 3 times 2 is 6. X times x is x squared. Again, you have the same base x, so you add exponents. 1 plus 1 is 2. Problem 33. X squared, y cubed, x to the 4th, y squared. And so this is equal to, I have the same base, x. So let me add exponents. I'm multiplying, so let me add exponents. 2 plus 4 is 6. I have the same base, y. So let me, and I'm multiplying, so let me add exponents. 3 plus 2 is 5. Let me do problem number 35. Five a cube minus 2a cube. Positive times negative is negative. 5 times 2 is 10. I have the same base a, so add exponents. 3 plus 3 is 6. Negative 10, a to the 6. 37. Two cube times 4 square over 3 square times 2 to the 4th. In exercises 37 through 60, simplify the expression. Okay, so I have here a 2 cube times 4 squared over 3 squared times 2 to the 4th. So I have 3 2's. I cancel 3 of these 2's. Only have 1 2 remaining. So this is equal to 4 squared, 16, over 3 squared, 9, times 2. 16 divided by 2 is 8. So your answer is 8 over 9. $39. 5 cube minus negative 5 cube. 5 cube is 125. Negative 5 cube is a negative 125, which makes that a plus. 125 plus 125 is 250. 40. To the 4th plus negative 2 cube. To the 4th, well, 2 times 2 is 4 times 2 is 8 times 2 is 16. Negative 2 cubed. Negative 2 times negative 2. Positive 4 times negative 2. Negative 8. 16 minus 8. 8. 41. 3 squared times 2 cubed. 3 squared is 9. 2 cubed is 8. 9 times 8, 72. 43. 2 cubed plus 3 squared. 2 thirds to the 5th. 2 cubed, 8. 3 squared, 9. Over 2 to the 5th. 3 to the 5th. 8 plus 9 is 17. 2 to the 5th is 32. 5 times 5, 2 times 2, 4 times 2, 8 times 2, 16 times 2, 32. 3 to the 5th, 3 times 3, 9 times 3, 27 times 3, 81 times 3, 243. So this is equal to 17. That's right, 17 is 17 over 1 times 32 over 243. And so this is equal to 17 times 32, 544 over 243. And that's your answer. Let me do 45 minus -2, -2 squared. Minus a -2. -2 squared is 4. Minus times minus is plus. 2 times 4 is 8. Let me do problem 47. -5 squared, -2 cubed. -5 squared is 25. -2 cubed is -8. Negative times negative is a positive. 25 times 8 is 200. 49. -2, 2 cubed, -2 squared. So this is equal to -2 times -2 cubed is 8. -2 squared is 4. Negative times positive is negative. 2 times 8 times 4 is 64. 51. And so this is the same as 2 cubed over 3 cubed times 1 over 8 times 3 squared, which I'll write as 3 squared over 1. 3 cubed divided by 3 squared is 3. 2 cubed is 8. Divided by 8 is 1. And so this is equal to 1 over 3. 53. Two-thirds squared (9 over 16). 2 squared over 3 squared times 9 over 16. 2 squared is 4. 3 squared is 9. The 9's cancel. 16 divided by 4 is 4. So this is equal to 1 over 4. 55 2 cubed minus negative 2 squared, 8 minus a negative, so 2 cubed is 8, negative 2 squared is 4, 8 minus 4 is 4. 57 minus negative 2 cube minus 4 cube. And so, negative 2 cubed is negative 8. 4 cubed, 64. Minus and a minus is a plus 8. 8 minus 64, negative 56. 59. Negative 3 cubed plus negative 3 cubed. 3 cubed is 27, and then negate. Negative 3 cubed is, well, negative 27. Negative 3 times negative 3 is positive 9, times negative 3 is negative 27. Negative 27 minus 27 minus a negative 54. 61. In exercises 61 through 70, simplify the expression using the power rule. So this is x, y squared, squared. So let me raise each of these to the power 2. So it's x squared times y squared squared. Well, I have a base to a power, so let's multiply exponents. 2 times 2 is 4. So x squared y to the 4. Let me do problem 63. Five a square b cube squared. So this is equal to 5 squared, 25, times, or maybe I'll just write this. This is equal to 5 squared times a squared squared times b cubed squared. Just raising each of these to the power 2 inside the parentheses. 5 squared is 25. A base to a raised to an exponent raised to an exponent. You just keep the same base, a, multiply exponents. 2 times 2 is 4. Base to an exponent. Keep the base b and multiply exponents. 3 times 2 is 6. 25, a to the 4, b to the 6. 65. Negative 2 a square b square to the 4. Raise everything to the power 4. Negative 2 to the 4. A square to the 4. B square to the 4. Negative 2 to the 4. Well, negative 2 times negative 2, positive 4 times negative 2, negative 8 times negative 2, positive 16. Multiply exponents. 2 times 4, 8. Multiply exponents. 2 times 4, 8. So 16, a to the 8th, b to the 8th. 67. Negative 2 x squared y square 2x. So let's raise each of these inside the parentheses to the power 2. Negative 2 squared is 4. X squared squared, multiply exponents. 2 times 2 is 4. Y squared is y squared times 2x. 2 times 4 is 8. I have the same base, x, add exponents. 4 plus 1 is 5, y squared. '69, 2x square cube cube. So this is equal to 2 cube times x squared cubed over 3 cube. 2 cubed is 8. X squared cubed is x to the 6. 3 cubed is 27. 71. Negative 2a to the power of 4 equal to negative 16a to the 4th. In exercises 71 through 80, determine whether the statement is true or false. Well, negative 2a to the 4th is negative 2 to the negative 2 to the 4 times a to the 4th, which is 16a to the 4th. And that is not the same as negative 16a to the 4th. And so this statement is false. Let me do problem 73. Negative 3b cubed, is that equal to, and I guess I should put a little, because it's asking, is it a true statement? So let's put a little question mark there. Is this a true statement? Negative 3b cubed. Well, negative 3b cubed is negative 3 cube b cube, which is a negative 27 b cubed. Negative 3b cubed is negative 3 cubed b cubed, which is 3 cubed is 27 b cubed. So these are equal. And so this is a true statement. So yes, these are both the same. 75. Negative 2 p squared all to the power 4. Is this equal to 16p to the 6? Negative 2p squared to the 4th is negative 2 to the 4th. P squared to the 4th is positive negative 2 to the 4th. Negative 2 times negative 2, positive 4, times negative 2, negative 8, times negative 2, positive 16. I have this a base to an exponent raised to an exponent. So I keep the base p, multiply exponents. 2 times 4 is 8. This is not the same as 16p to the 6th. Therefore, this statement is false. 77. X squared y to the power 4 x to the 4 y to the 4. X squared y to the power 4 is equal to, raise each of these inside the parentheses to the power 4. 2 times 4 is 8. Well, x to the 4th is not the same as x to the 8th. And so again, this is false. 79. Four squared minus y squared, 16y squared. Well, 4 squared negative y squared is equal to 4 squared is 16. Negative y squared is y squared. So yes, indeed, these are equal. So this is a true statement. 81. 3x, 2x squared, 4x squared, 3x. In exercises 81 through 88, simplify. Okay, so let's look at this. 3 times 2 is 6. X times x squared is x cubed. 4 times 3 is 12. X squared times x is x cubed. 6x cubed plus 12x cubed is 18x cubed. And that is your answer. 83. Negative 2x y x squared y cubed minus 5x to the 5th xy squared squared. So let's raise each of these inside the parentheses to the power 3. So I have x squared cubed y cubed minus 5x to the 5th x squared y squared squared. So this is a negative 2xy. 2 times 3 is 6 minus 5x to the 5th x squared. 2 times 2 is 4. So I have a negative 2. I have the same base. I multiply, so add exponents. 1 plus 6 is 7. I multiply, I have the same base, so add exponents. 1 plus 3 is 4. I have the same base, I'm multiplying, so add exponents. 5 plus 2 is 7. Y to the fourth. Negative 2x to the 7 minus y to the fourth minus 5x to the 7 y to the fourth is a negative 7 x to the 7 y to the 4. 85. Five, a to the 7, 2a squared minus 3a cubed, 7a to the 6. Five times 2 is 10. 7 plus 2 is 9. 3 times 7 is 21. 3 plus 6 is 9. 10a to the 9 minus 21a to the 9, negative 11a to the 9. 87. Eight x cubed y squared minus 2x xy squared. So this is equal to 8x cubed y squared minus, raise each of these inside the exponent to the power 2, so x squared y squared. 8x cubed y squared minus, I have the same base, I'm multiplying, so add exponents. 1 plus 2 is 3. 8x cubed y squared minus 2x cubed y squared is 6x cubed y squared. 89. In exercises 89 through 94, find the area of the figure. So I have here a rectangle, and it's a 2x cubed and a 3x to the 5th. So just recall, if this is a length and a width, then the area is length times width. And so length times width, 2 times 3 is 6. I have the same base and I'm multiplying, so I add exponents. 3 plus 5 is 8. Let me do problem 91. So I have here a 4m cubed, and this is a square. And so the area of a square, same as the area of a rectangle. Let's say this is a side, then the area of a square is just, maybe let's put x's, because my s's look like 5s. Maybe we'll call this x. So then the area of a square is the side squared, whatever I want to call it. Okay, it doesn't really look like a square that much. That looks a little bit better, not much better, but Okay, so the area of a square is just 4m cubed squared. 4 squared times m cubed squared. 4 squared is 16. I have a base to a power, multiply exponents. 3 times 2 is 6. 93. Three to the 4 over 2. Okay, so first, if I have a circle of radius r, then the area of a circle is pi r squared. And so the area is pi times the radius, 3a to the 4th, over 2 squared. So the area is pi times 3 squared times a to the 4th squared over 2 squared. So a is equal to 3 squared is 9 pi 8 square a to the 4th squared. The base to an exponent to exponent. Keep the base. Multiply exponents. 4 times 2, 8 over 2 squared, 4. And that is the area of your circle. 90, that's let's see, that's the last one of this section. Yes. So that's the last problem in this section. Maybe I should have just written it here. 9 pi a to the 8 over 4. So it doesn't have to go to another page. So that finishes off section 5.1. Okay. Yeah, I think we have enough time for section 5.2 on polynomials. So section 5.2, polynomials. So an example of a polynomial would be something like negative 15 x cubed plus 7x squared minus 12x plus 4. Okay. So this is an example of a polynomial. It consists of, well, a whole bunch of terms. So these are terms that I keep adding together. Each of these terms will consist of, let's look at, let's say 7x squared. Okay. Well, each term consists of maybe I'll make this a little bigger. So let's say 7 times x to the 4. So this is a term, and it'll consist of, well, a variable part, this variable part consists of some variable base so you have a base that is some variable. And this variable will be to some whole number exponent. And then the other part of this that you're multiplying is your numerical coefficient. Which just consists of some number. Usually, since it consists of a number, we just call it the coefficient, rather than, because it's sort of redundant saying it's a numerical coefficient, since it's a number. So let me say this sort of again. A polynomial in the variable x So a polynomial in the variable x, let's denote it by p of x for polynomial. The subscript of n here will actually be something called the degree of the polynomial. It will consist of, well, some constant times x to the n, another constant times x to the n minus 1, plus some constant times x, plus some other constant, where each of these coefficients are constants, real numbers. This will be a real number polynomial, and n is a whole number. Let's assume that the leading order coefficient is not 0. So if a sub n is not 0, and we're assuming that when I write this, then the number n is called the degree of the polynomial. Okay, let me actually be a little bit, let me give you an example, and then I'll give you sort of a better way or more detailed explanation of the degree. So let me give you an example. Let's say the polynomial is 21x to the fifth minus 4x squared plus 7. Then the degree of my polynomial is just the highest power here, which in this case is 5. So it's the highest power. Suppose instead of having just one variable, we have more than one variable. Well, let me just give you the definition of the degree of a term. So suppose I have seven x cubed y squared z to the fifth. So I have maybe more than one variable. So this is a term because it's just a whole bunch of things multiplied together. So a term just involves a whole bunch of things multiplied together. One of the things being multiplied is some constant, and the other things being multiplied together are variables to whole number exponents. Then the degree of this term is found by just adding all the exponents of the variables. So 3 plus 2 plus 5, 10. That's the degree of this term. Let me give you another example. Two cubed x to the fourth y. Then the degree of this term is found by just only looking at the variable parts and adding exponents. 4 plus 1 is 5. I don't worry about the exponent on the constant. The degree of a polynomial is just the largest degree of any of its terms. So the degree of a polynomial is equal to the maximum of the degrees of the terms in the polynomial. So let's do an example. Say the polynomial is, 18x squared 14x y cubed minus 23 x squared y. Well, let's find the degree of this polynomial. So first, let's find the degree of 18x squared. Well, that's just going to equal 2. The degree of 14x y cubed, found by adding the exponents. 1 plus 3 is 4. The degree of 23x squared y, add exponents. 2 plus 1 is 3. Therefore, the largest of the numbers, 2, 4, and 3, is 4. So the degree of your polynomial is 4. Okay. I guess I should say that sometimes we capitalize degree, sometimes we keep it in lowercase. Depends on the book. Okay, let me give you some more terminology. A monomial is a polynomial with one term. A binomial is a polynomial with two terms. A trinomial is a polynomial with three terms. The constant term, well, a polynomial is called a constant polynomial if the degree of the polynomial is 0. A linear polynomial is a polynomial of degree 1. A quadratic polynomial is a polynomial of degree 2. A cubic is a polynomial of degree 3. A quartic is a polynomial of degree 4. Sometimes it's also called a biquadratic instead of a quartic. Quintic polynomial of degree 5. And you can keep going up, but, etc. Next, the leading order coefficient, usually denoted by LOC. This is the leading order coefficient. This is the coefficient of the term in the polynomial of largest degree. So that term in the polynomial that has largest degree, whatever the coefficient is of that, that's called the leading order coefficient. Now, if all of them, if there is more than one term that has the same largest degree, then it's the one that would come first in alphabetical order. So, first degree using lexicographic ordering. How you would read it if you were putting something into the index of a book or in a library, how you would uh, read it from a dictionary, how it would be listed. Okay. So it would be the one that would be first in the order. Okay. So things like X goes before Y. So if you had like a something like X cubed term and a Y cubed term, you'd look at the X cubed term because X comes before Y. Next, a monic polynomial is one whose leading order coefficient is equal to the value 1. Okay. That's pretty close. We'll have to do examples, but that's the end of the time. Okay, so I guess I'll it for today, and I'll see you guys tomorrow.